Hi everybody, we're going to start today by treating and grading the indicators lab. So please pass around the red pens and we're going to get started. So the total for this lab is going to be 15 points. The heading, purpose, procedure are 1 point each as usual. The data table is 4 points as long as the data table is filled with different colors, then that's okay. The questions. The first question is worth 2 points. It asked you whether the unknowns were acidic, basic, or neutral, so half a point for each one, and this is graded on accuracy. Unknown number 1 is neutral, unknown number 2 is acidic, unknown number 3 is basic, and unknown number 4 is acidic. Second question asked you to identify each of the unknowns based on the 4 substances that you were given. So they're half a point each, and again, it's based on accuracy. So unknown number 1 is methanol, since it was closest to being neutral. Unknown number 2 is hydrochloric acid, because it was acidic and it was actually a stronger acid than number 4. Unknown number 3, because it's basic, then that would be ammonium hydroxide. And unknown number 4 is vinegar, because it's acidic, but it's less acidic than the HCl. Next question, the answer is D, that's 1 point. Number 4, the answer is C, that's 1 point. Number 5, the answer is D, that's also 1 point. And then finally, number 6, the answers are both A and C, that's worth a point. So if they only picked A or C, then that's half a point. Again, the total is 15 points. You can pause this video until you are done grading and then pass them to the front, please. All right, let's start our notes. So please flip in your packet to the page where it says Titrations. So today we're going to talk about titrations, specifically acid-base titrations. A titration is a lab technique. It's an experiment that you do in the lab. The point of it is to find out the molarity of a solution. And so let's say you have some HCl sitting in the lab and it does not have a concentration on it. If you want to know the concentration of it, then you titrate it. And titrations don't have to be a reaction between acids and bases. They could be other reactions, but most of the titrations, or the most popular use of titrations, is for reactions between acids and bases. So back to our HCl of unknown concentration, what you do is you measure a certain amount of your HCl, let's say 10 milliliters. You put it in an Erlenmeyer flask, and you titrate it with a base. And that base that you titrate it with obviously has to be known, so you need to know the concentration of it. And you keep adding the base until the reaction is done, until it's neutralized. You figure out how much base you've added, and you can figure out how many moles of base you used, and therefore how many moles of acid you use, and you can figure out the concentration. So the idea of titration is that you basically add a measured volume of a solution of known concentration, that's what we call the titrant, what you titrate with, into the solution being analyzed, which is called the analyte, which is something that you analyze. So in our example, the HCl that you didn't know the concentration of, that would be the analyte, what you're analyzing. The base that you use to titrate it would be the titrant. Now, usually, I'd say 95% of the time, not 100% of the time, but 90 or 95% of the time, the acid goes in an Erlenmeyer flask. Now, we use an Erlenmeyer flask so that we can swirl it easily without it splashing outside. So a beaker would not be very good for a titration. Usually with the acid, we also add an indicator. Now, we just talked about indicators yesterday, so there are a variety of different indicators. Some turn just from one color to another. Some turn all the colors of the rainbow. And so usually you want to pick an indicator for this one that only has 2 colors, so that you can see a definite change at your end point of the reaction. You don't want something like universal where it goes from, red to like a little reddish orange to a little dark orange to an orange yellow. It's kind of hard to tell when to stop when it's like that. Whereas something like phenolphthalein, where it goes from colorless to pink, then once it turns pink, then you know that you're done with the reaction. So again, the acid and the indicator typically go in an Erlenmeyer flask here. And then you use a burette. If you remember, a burette looks like a really, really long graduated cylinder. So it's very long. It has graduations here in terms of volume. It's kind of a little bit different from a graduated cylinder in the sense that right here is your 0 milliliters at the top, and all the way at the bottom that's 50 milliliters. So it actually measures the volume that you dispense as opposed to the volume of liquid that's inside. So what you do is you fill it all the way at the top until it says 0. That means you haven't dispensed anything. Then you slowly open this valve, and if it's parallel, that means it's open. If it's perpendicular, that means it's closed, and I'll show you tomorrow what that looks like. You open it and you let the base go into the acid literally drop by drop, very, very slowly. And as you're adding the base, you need to swirl this so that the acid and the base mix together. And so the volume increases as you go down, so it starts at 0 that you've dispensed, then you dispense 1 mil, then 2 mils, then 3 mils, then 4 mils, and so on. And you keep adding the base until the color of the indicator changes. So if you're using phenolphthalein, which we're going to be using tomorrow, for example, in our lab, it's going to go from colorless to pink. So once it turns a very slight pink, the lightest hint of pink that you see, that's when you stop and you close that valve, and then you read how much volume of base that you've dispensed. So let's say, for example, you've dispensed 20 milliliters of base, and it's 1 mole. So if you know the volume and you know the concentration, then you can calculate how many moles of base you used. If you look at your chemical equation with the acid and the base, you can use the molar ratio to go from moles of base to moles of acid. So you can calculate the moles of acid you used. And if you have the volume of the acid that you've put in your Erlenmeyer flask, if you have the volume and the moles, then you can figure out what the concentration is. So here's what a typical titration curve looks like. It looks kind of like an S. So at the very beginning, if you were to measure the pH that's in your Erlenmeyer flask where your acid and your indicator is, it's acidic. And so the pH should start very low, depending on what the pH of your original acid is. Then as you add base, so this is the pH, this is your volume of base that we added. So our example here is NaOH. So as you add NaOH, you increase the pH because NaOH is basic, and obviously what's in your flask is acidic. So it becomes less and less acidic, and so the pH increases very, very slowly. Then suddenly it shoots up. And that's really why you need to do it drop by drop, because literally one drop would be, let's say, a pH of, for example, 3. The next drop would make it a pH of 9, for example. And so it's a dramatic increase with very little change in the volume of NaOH that's added. And then after it shoots up, then again it increases, but very, very slowly, and then eventually it levels off and stays the same. A couple of points that are, well, one really important point on this curve that's very important is your equivalence point. The equivalence point is where you see in your curve an inflection here and an inflection here, so halfway between the two inflection points. That's your equivalence point. The equivalence point is where exactly enough titrant has reacted with the analyte. So that means equivalent amounts of acid and base have reacted together based on the stoichiometry or the molar ratio. So if it's a 1-to-1 ratio, then the moles of acid are equal to the moles of base. If it's a 2-to-1 ratio, then the moles of acid to moles of base are 2-to-1, and so on. So that's when basically you have no limiting reactant. Your acid has completely reacted with the base. No excess reactant, no limiting reactant. Notice that this is not always at a pH of 7. Some titrations will end at pH of 7, but some won't. And so that is not always at a pH of 7. Sometimes your products are neutral, other times your products are acidic or basic. But the original reactants, so the acid and the base originally that you're reacting together, have been all used up at the equivalence point. Another point that is important is the end point. So now this is not necessarily part of the graph, but the end point is where the indicator that you chose turns colors. And that's going to be different depending on which indicator you choose. For example, if you choose methyl red, that changes at a pH of 5. If you choose phenolphthalein, that changes at a pH of 9. So every indicator changes at a different pH. What you want to do is pick an indicator that will change at a pH close to what the pH would be at your equivalence point. So the pH at the endpoint should be close, but not always the same exact pH as the equivalence point. For example, let's say you take HCl and NaOH and you react them together, and the pH at the equivalence point is pH of 7, as an example. It doesn't always have to be at 7, but let's say it's 7 this time. I can pick phenolphthalein, for example, as an indicator. Phenolphthalein doesn't turn until a pH of 9. So why is it okay if my equivalence point is at a pH of 7? Why would it be okay to pick an indicator that would turn at a pH of 9? The reason is, if you look at this curve, there's a very, very, very dramatic change in pH with very little change in the base. So if you look like right here at this point to this point in the graph, almost a negligible amount of base will turn it, let's say, from pH of 3 to pH of like 10, something like that. You know, from here to here, that's a very, very slight change in the volume. And so if this is where your reaction ends and you choose an indicator that will turn right here, from here to here, there's not much change in volume. It may be a drop or so, which will not really change your volume. So if your equivalence point is at a pH of 7, you can choose an indicator that will turn anywhere between like 4 and 9, let's say. If your equivalence point will be at a pH of 9, then you could pick an indicator that would turn anywhere between like 7 and let's say 11 or so. Any of those would be fine because of that dramatic change in pH with very little change in the volume. And that's why, again, when you do a titration in the lab tomorrow, you have to do it really drop by drop, because one drop would make a big difference in the pH suddenly. Alright, so we said the whole point of a titration is to figure out usually the concentration of solution that you don't have, the concentration of. You know what it is, but you don't know its concentration. So let's try an example here where we can actually use data from the titration. So it says in a titration of 40 milliliters of acetic acid is the active ingredient in vinegar. So vinegar is about 3% acetic acid. If you've ever tasted vinegar, it's really strong, right? It's very sour. It Imagine that's 97% water and only 3% acetic acid. So imagine if you were to drink, a sip of 100% pure acetic acid. That would be very, very strong. But again, relatively, it's a weak acid. It's considered one of the weak acids. Anyway, the end point is reached when 35 milliliters of 0.5 molar NaOH is added. So in your burette, you add NaOH, and it's 0.5 molar, and you keep adding until it's 35 milliliters. The color changes when you've added 35 milliliters. In your Erlenmeyer flask that you start with, you had 40 milliliters of the acid with the indicator in there. So you want to calculate the concentration of the acetic acid. So first thing you want to do, since it's talking about a chemical reaction between an acid and a base, is you want to write the equation for it. So acetic acid is HCH3COO. You add to that NaOH, and that yields. Remember, neutralization reactions are basically a special kind of double replacement. So the two outer ones go together, so H and OH form H2O. And then the two middle ones together, remember the metal goes first, so Na, then CH3COO. It's already balanced, they're all 1:1 to 1:1 ratio. Next, this is optional, but I like to do it. I like to write down what I have and what I'm trying to find. So I have 40 milliliters of the acetic acid. So I'm going to put 40 milliliters here. I'm trying to find its molarity. The NaOH is 35 milliliters, and I'm told that it's 0.50 molar. All right. We actually have done this before. We called it solution stoichiometry. So we've done these calculations before. So let's see if you can remember what to do. In any stoic problem, first thing you do, there's 3 steps. The first step, after you write your equation, of course, but the first step of the calculation is calculate the moles of the substance that you have information about. So the only substance we have enough information about is NaOH. We have the volume, we have the molarity, so we can calculate the moles. Second step is to calculate the moles of the substance you're interested in. So we're asked about the molarity of the acetic acid, so we want to calculate the moles of acetic acid. And then finally, you answer the question, in this case, to find the molarity of the acetic acid. So let's go step by step. First step is we want to figure out the moles of NaOH. So since we have the volume, we have the molarity. We know that molarity is moles per liter. So we can say that 0.50 molar is equal to X moles of NaOH over liters would be 0.035 liters. So that gives us 0.0175 moles of NaOH. So we found moles of the substance that we have information about. Next is to find moles of the substance we're interested in. So our next step would be to find moles of the acetic acid. So we have 0.0175 moles of NaOH. So to get moles of acetic acid, you put moles of NaOH on the bottom. And moles of acetic acid on top. And it's a 1:1 based on the molar ratio that's here and here. So that equals 0.0175 moles of my acid, the HCH3COO. Last step is to actually answer the question. The question was, what is the molarity of the acetic acid? So next I'm going to say molarity is moles per volume again, moles per liter. So if I want the molarity of the acetic acid, I know that it's 0.0175 moles divided by my volume is 40 milliliters of acid. So change that to liters, so that's 0.04 liters. And it's 0.0400 liters with sig figs. So that ends up being 0.44 molar. And that's our answer. I would highly recommend that you star this example. You will see it again, hint, hint. So make sure that you really star that first example and use it and look over when you're studying and preparing for stuff. Let's try another example. So example 2 says a volume of 35 milliliters of 0.1 molar calcium hydroxide neutralizes a 45 milliliter sample of hydrochloric acid. What is the concentration of the HCl? So similar to the last problem, very similar. You have an HCl solution and you don't know its concentration, but you do know that it's 45 milliliters. So you titrate it with 0.1 molar calcium hydroxide, and it takes 35 milliliters to get the indicator to turn colors. So you want to know the concentration. First step, let's write our equation. So calcium hydroxide is ionic. Calcium is 2+, hydroxide is OH minus. So it's Ca parentheses OH2 plus HCl yields. Again, this is a fancy double replacement, so you put the two middle ones together, so H and OH, that forms water. It doesn't matter, there's two of them, that's what balancing is for. So that would make H2O, and then you put the two outer ones together, so we have chloride and calcium chloride. This is Ca2+, this is Cl minus, so the product is CaCl2. You always have to write neutral compounds. Let's balance it. You need 2 HCl and then 2 H2O. Next step is optional. I like to do it. I like to write down what I have and what I'm looking for. So I have 35.0 milliliters of the calcium hydroxide, and it's 0.100 molar. My HCl, I know I have 45.0 milliliters, and I'm trying to find its concentration. So when it comes to the calculation, first step is find the moles of the substance that you have enough information about. So calcium hydroxide, we have the volume and we have the molarity, so we can figure out the moles. So again, molarity is moles per liter. So I know it's 0.100 molar. That is equal to X moles of CaOH2 over 0.0350 liters. So that gives me 0.00350 moles of calcium hydroxide. My next step is to find the moles of the substance that I'm actually interested in. So that would be the HCl, since I'm trying to find its concentration. So to link between two different substances, you use moles and use the molar ratio. So I have 0.00350 moles of calcium hydroxide. So on the bottom, I'm going to put moles of calcium hydroxide On top, I'll put moles of HCl because that's what I'm looking for. And from the molar ratio from the equation, it's a 2 to 1. So I'll put 2 on top and 1 on the bottom. So that is equal to 0.00700 moles of HCl. My last step is to answer the question, which is the molarity of the HCl. So again, you can say molarity is moles per liter. So the molarity of the HCl would be the moles of HCl, which is 0.00700 moles, divided by the liters. We have 45 milliliters, so that's 0.0450 liters. And so that ends up being 0.156 molar. All right. Let's try the last example. It says I have a volume of 28.3 milliliters of 0.12 molar aluminum hydroxide that neutralizes a 0.37 molar sample of sulfuric acid. What volume of sulfuric acid is needed for the titration? So this time it's just slightly different. This time my sulfuric acid, I know the molarity of it. I just want to know how much of it would be neutralized by my aluminum hydroxide. So I'm looking for the volume as opposed to the molarity. So as always, we're going to write our equation. Aluminum hydroxide, that's ionic. Aluminum ion is 3+, hydroxide is OH minus. So Al parentheses OH3 plus sulfuric acid is H2SO4 yields. Put the two middle ones together so that, the two middle ones together, that gives you water, and the two outer ones together will give you aluminum sulfate. So water is H2O, and then the two outer ones, aluminum sulfate. Aluminum is 3+, sulfate is 2-, so Al2 SO4 3. Let's balance it. So we need 2 aluminum, so we'll put a 2 here. We need 3 sulfates, so I'll put a 3 here. And so that means we would need 6 waters. I'm going to write down what I have. I have 28.3 milliliters, and I know that it's 0.120 molar. My H2SO4, I know it's 0.37 molar, and I'm trying to find the volume. All right, so first I'm going to find the moles of the substance that I have information about. That would be the aluminum hydroxide. So molarity is moles per liter. I know that it's 0.120 molar, so that equals X moles of aluminum hydroxide over the volume of aluminum hydroxide, which is 0.0283 liters. So that gives me 0.03396 moles of AlOH3. You can round it at this point. I like to round at the very end with my sig figs. Next, find the moles of the substance that you are interested in, which is the H2SO4, so use the molar ratio for that. So 0.003396 moles of AlOH3. On the bottom, you're going to put moles of AlOH3. On top, you're going to put moles of sulfuric acid. That's a 4, not a 44. Sorry. My stylus is not working too well. From the molar ratio from the equation, I know that there's 3 moles of H2SO4 for every 2 moles of aluminum hydroxide. So that equals 0.00510 moles of H2SO4. And then my last step is to answer the question. I wanted the volume. So I have the molarity, I have the moles, I can figure out the volume. Molarity is moles per liter. And so I know it's 0.37 molar is equal to 0.00510 moles over X liters. And I solve for the liters. It turns out to be 0.014 liters, and that's my answer. All right, that's it for today. Hope you have a wonderful rest of your day.